Okay, so why don't we get started? Welcome everyone to this week's webinar talk sponsored by CDAC, the Chicago DOE Alliance Center, our NNSA Stewardship Science Academic Alliance Center, headquartered here at the University of Illinois at Chicago. It's a pleasure to introduce today's speaker, Priscilla Rosa from the Quantum Group at Los Alamos. Priscilla's area of research is strongly correlated quantum materials and the various types of emergent phenomena found in these systems, including how those phenomena can be induced or modified by pressure, which I hope she'll tell us about today. Priscilla has a PhD from the University of Campinas in Brazil, which she received in 2013. She then moved to UC Irvine as a postdoc before joining Los Alamos as a director's postdoctoral fellow, a position she had from 2015 to 2016, and after that joined the staff there at the lab. So her title is Strongly Correlated Materials Under Pressure. Welcome, Priscilla.
Thank you very much, Ross, for the kind introduction and for the kind invitation. I'll start by giving a brief overview of the goal of our group regarding strongly correlated materials under pressure. And then I'll focus on a particular example of uranium tellurium-2, which is a newly discovered superconductor. So we need to start somewhere, right, with organizing principles. So let me tell you a little bit of the organizing principles for the work I'm going to present here and overall in our group. The organizing principles to search and discover new emergent phenomena. They will be a combination of strong electronic correlations, and in particular, F-electron systems are really prototypical materials to exhibit such strong correlations. New phase spaces, because of course, if you're looking at a phase space that no one has looked before, chances are that you may discover something new. Extreme conditions, as the audience know very well, including high pressures, high magnetic fields, and low temperatures. And finally, topology, which is a somewhat new or recent concept in condensed matter physics, and I'll touch on that later on. So on F-electrons under pressure, and in particular, the emergent phenomena of superconductivity. And this can be really nicely seen in the so-called Doniak phase diagram. Here we have temperature versus the exchange coupling between F-electrons and conduction electrons times the density of states at the Fermi level. So at the very left of the diagram, we have an antiferromagnetically ordered state usually. And if we can increase the coupling J, or the density of states, or the combination of both, then we'll go towards a maximum of T now of the antiferromagnetic order, and this order will be suppressed towards a quantum critical point. So we have a second order phase transition being suppressed to 0 temperature. At this point, we have something that is not Fermi liquid, and we have really strong fluctuations. I like to think of this as a buildup of entropy that has to be relieved in some way. And often it's the case that superconductivity is the way nature chooses to relieve this entropy and create a new ordered state around this quantum critical point. And in fact, that is the case in many F-electron materials. Here is a prototypical example discovered at LANO, cerium rhodoninium 5. We can see here the temperature pressure phase diagram. Again, at low pressures, the system orders magnetically. Under pressure, the hybridization increases, or the coupling J increases. And this material is driven towards a quantum critical point around which D-wave superconductivity emerges. And I want to make this point that this is a D-wave superconductor. It's a singlet, L equal 2 order parameter, because later on we're going to see other examples that are not singlet or not D-wave. So this exists in nature, and it really also provides us an organizing principle to look for quantum critical points. So from the experimental point of view, we can explore or investigate the systems under pressure using a variety of techniques. And here in our group, we use not only the standard, let's say, electrical resistivity in Hall, but also AC calorimetry, which is really important, and we'll see this later on as well. When we have a superconducting state and we want to look for transitions that occur below the zero resistance onset. Another very nice development, recent development, is thermal power measurements under pressure. That really allows us to investigate quantum criticality very well. And more recently, I have been very excited about thermal expansion under pressure. So we know that the so-called Grunizing parameter, which is the ratio between thermal expansion and heat capacity, diverges at a quantum critical point. But really, thermal expansion measurements under pressure are really challenging, and conventional capacitance dilatometers cannot be used. So very recently, we have been working on thermal expansion measurements using the optical fiber approach. In this case, we have a fiber Bragg grating here, illustrated at the bottom. And if you glue a sample to this fiber Bragg grating and the sample expands or contracts, then we can see the change in the wavelength reflected by the grating. And that will give you the delta L over L of the sample. So those are all very exciting ways of exploring F-electron systems under pressure. But today I want to mention another aspect of superconductivity, and that is the so-called topological superconductivity. So a brief overview of this concept, which really starts in mathematics and in geometry, when small local perturbations cannot change the shape of objects, right? So this is one topological classification in geometry. For example, the number of holes in one object. If you have a ball that has 0 holes, if you have donut that has 1 hole, and you cannot really transform a ball into a donut without punching a hole through it. So in this sense of topology, we have a classification of the shape of objects. But more recently, this concept was also extended to condensed matter physics. And here, how can we think of this difference? Well, we have to look at the band structure of the material. So in one of the simplest examples, when you have a system with inversion symmetry, you can calculate the so-called Z2 topological index. And that will be a product of the parities at high symmetry points. So looking here at the figure on the left, we have a simple, conventional or trivial insulator where this product will be +1. On the right side, when you have inversion symmetry driven by spin-off recoupling, then this product of parities will be -1, and you have a topological insulator. And this state is very interesting because it means that one has to have surface states that are protected by time reversal symmetry in this case. And you can envision the surface of a material with spin textures on their surface. And because this spin texture is protected by this particular symmetry of the system, it can be envisioned to be used in dissipationless transport, for example, in spintronics, or perhaps the most exciting aspect is to have this topological insulator in proximity to a simple S-wave conventional superconductor where exotic quasi-particles called Majorana fermions may exist. And another class of materials in which these exotic particles could also exist in are topological superconductors. And just the same way we just described the topological classification of insulators, we can also define topological numbers for the occupied states in superconductors, but things get a little more complicated because we need to know, for example, if we have a quasi 1D, 2D, 3D system, if we have time versus symmetry breaking or not, and on top of all of that, nodes in the superconducting order parameter may also have their own topological classification. So things are a bit more complicated. But that's when a combination of experimental intuition and theoretical background will be important. We know that from the theory that spin triplet superconductivity is particularly prone to host topological states. And we know from experiments that uranium-based superconductors, or 5F or materials in general, tend to host spin triplet superconductivity. But we really need to take a step back to be able in the end to perform the topological classification. We need to know what the superconducting order parameter is. We need to know whether time reverse symmetry is broken. We need to know what the uranium valence is in the material, and we need information on the Fermi surface. So it's a really huge experimental effort, and we're very excited actually to be doing this type of research. And perhaps you can wonder why one is interested in finding these Majorana fermions or particles that are elusive and haven't been, there's no consensus, let's say, about their existence even. And that's because there is a really large effort right now in the US in particular with the National Quantum Initiative to really search for new ways of performing computation that goes beyond the conventional binary way. One predicted way is the so-called topological quantum computing, where one could use these Majorana particles, which have this interesting definition of being their own antiparticles, to create excitations that have a particular statistic called non-abelian statistics. So instead of, when you exchange these particles, instead of having plus or minus one, depending on whether you have fermions or bosons, you're going to have a phasing between them. So one can prepare, in principle, a quantum bit using a superposition of these Majorana modes and perform computations with the system. So this is really the end goal here. But again, we are at the very base of the materials pyramid, and we need to take a step back and understand the candidate materials. So let me tell you about one newly discovered contender. That's uranium tellurium-2. It crystallizes in this complicated crystal structure, and when I say complicated, it's because it's orthorhombic, which you see in a minute complicates things a little bit. But it has a very interesting crystal structure in the sense that you can see that along the A-axis, there are chains of uranium, and along the C-axis, there are ladders or dimers that stagger along the C-axis. So this material was known for quite a while, for decades, but it was only discovered to be a superconductor last year. So here's the reference, Nick Butch's group at the University of Maryland and NIST. They cooled down this material below 2 Kelvin, and they found out that it is a superconductor. So let me tell you first, in the normal state though, here's the magnetic susceptibility versus temperature. It's orthorhombic, so it's anisotropic. A, B, and C are not equivalent. But one thing to point out is that along the A-axis, we have a larger magnetic susceptibility, indicating that that may be the easy axis of this material, at least at ambient pressure. Here's the electrical resistivity. At high temperatures, we can think of the system as a incoherent system of felectrons, weakly correlated moments, but at low temperatures, hybridization sets in, and the system has a very low resistance until it goes to a zero resistance state. But a superconductor is also characterized by the Meissner effect. So panel B here has also the diamagnetic signal below about 1.6, 1.7 Kelvin. The heat capacity is very interesting too. Here we have a clear peak at TC, but it's interesting that at low temperatures, the Sommerfeld coefficient, or the low temperature extrapolation to zero temperature of the specific heat, is actually quite large. It's about half of the normal state gamma. I'll put a pin on this for now, and I'll come back to this later. It's still not very well understood why that's the case. Finally, NMR, or nuclear magnetic resonance on tellurium, shows almost no night shift through TC. And just recalling that if we have a spin singlet material, the night shift has to go to zero at zero temperature. If we have a spin triplet superconductor, we wouldn't expect a very large change at TC, and that's exactly what's seen. Though I need to point out that those first experiments were done in powdered samples, and these here are newer results on single crystals, and they do see a small drop in the night shift at TC, but again, it's a very small drop. It doesn't go to zero. It's consistent with a spin triplet superconductor with the so-called D vector of the superconducting order parameter pointing along the B axis. And more striking, I guess, at least to me, is this upper critical field plot versus temperature, where for fields along the A-axis, one has a small critical field. Again, fields along the easy axis may do that. However, when the field is parallel to the hard axis, meaning the B axis, the critical field is gigantic. It's much larger than the Pauli paramagnetic limit for spin singlet superconductors. So this is all consistent with the spin triplet superconductor so far. And again, those may be nearby a ferromagnetic instability, which was also put forward in the first science paper. And we're all very excited about this material. But now we want to squeeze it, right? We want to apply pressure to it. I must say that not only our group has done this, the measurements under pressure have been done by many groups. I just mentioned here one example. There are many others, which is again very, I think, exciting. So this is a temperature pressure phase diagram of this material. It's interesting that the TC, the superconducting transition temperature, decreases at first, and then it seems to increase and actually split into two. One of them increases, the other one decreases, and then at some pressure around 1.5 GPa, there is an abrupt change from the superconducting state to something that looks like a magnetically ordered state. And it's important to point out that these measurements were done both with resistivity and AC calorimetry. That's very important because if you have two superconducting states, you have to have a bulk thermodynamic probe to probe both of them. So this is here shown in panel B, for example, at 0.5 GPa, you can see clearly two peaks for the superconducting transition temperatures. When we saw some of these results, many questions started to arise. The first one is, how do these transitions extrapolate to zero pressure? And that's an important question because we want to know whether there are two transitions in this material, right? This will help us understand what the order parameter is. And the second question is, what really is happening in this pressure region around 1.5 GPa? It seems to be really first order like, and we wanted to explore this part of the phase diagram, especially because of the possibility of a quantum critical point. Okay, so these are results obtained in our group here in Los Alamos. So the first plot on the left actually shows an adiabatic heat capacity measurement, not in the pressure cell. Just to show that even at zero pressure, if you do a so-called pulse, heat pulse measurement, really close to TC, you can see two peaks. This is sample dependent, and again, this is an open question right now, and I'll get back to, I hope to get back to this at the end of the talk. But independent of the small variations that are observed, the two peaks are always there. And then we got this sample, or a sample very similar to this, with the clear two peaks, and we applied pressure to it. So here, this is the second plot. We can see TC1, TC2 at low pressures. And then as we apply higher and higher pressures, these two transitions actually cross each other. And you can see that TC2 starts to lose entropy, and TC1 starts to gain entropy. So this is really screaming to us that there are two transitions and they're competing. One is suppressed under pressure and one is enhanced under pressure. So we can really write down now a free energy, and this is not a microscopic model. This is just, again, a very phenomenological model of two competing order parameters, psi1 and psi2, and epsilon here is pressure. So at some pressure when epsilon is 0, which means experimentally roughly 0.2 GPa, these two transitions are accidentally degenerate. But as you increase pressure, one of them, psi1 is enhanced and psi2 is suppressed. And from this simple free energy, we can actually get to the conclusion that the jumps at the sum of the jumps at the superconducting transition temperatures, they have to, the sum has to be constant. And actually you can see in this plot, the blue squares, that is correct for low pressures. At higher pressures, this is not true anymore, that doesn't hold, and that it's likely to be due to the fact that we're going towards a magnetic instability. And in fact, at 1.47 GPa, we can see another peak coming up. So we have superconductivity and a second peak above it, which is most likely due to magnetism, even though we don't have yet magnetic diffraction data on these samples. It's ongoing, underway, but we don't have that confirmation. But let's assume for now, it is a magnetically ordered state. It's interesting that when that state comes up, TM1, the superconducting transition from the bulk heat capacity measurement starts to broaden first, and it's at lower temperatures than the onset or offset even of the zero resistance state. So this tells us that these two states are competing with each other very dramatically, actually. And this indicates that there is no microscopic coexistence of these two states. And the figure here on the right is at slightly higher pressures, showing that the superconducting bulk transition actually disappears very abruptly indeed. And that's likely why the previous results could not see this evolution of the bulk superconducting transition. So let me tell you about the phase diagram that we can construct with this. This is the temperature pressure phase diagram. And we can see again that at low pressures, the two superconducting transitions cross each other. One of them is enhanced, the other one is suppressed. And it's interesting that we can assign two critical pressures. First, the critical pressure that is in extrapolation of the magnetically ordered state, PC1, and then the second one, PC2, where this is extrapolation of what we think is magnetism meets the superconducting state. You may be familiar with this plot at this point, right? I showed you the example of cerium, rhodium, indium-5 a little bit earlier today. And there are a lot of similarities, actually, indeed. We have a non-Fermi liquid-like state above this quantum critical point in cerium, rhodium, 5. And here in uranium, tellurium 2, we have a very similar non-Fermi liquid behavior that is not T-squared around PC1. Let me take this comparison a little further. This is the phase diagram of cerium, rhodium, 5 as well, both with heat capacity and resistivity measurements. And you can in fact see that the superconducting transition temperature from resistance is higher than that from heat capacity, similar to uranium, tellurium 2 as well. And in this coexistence region, actually, the critical currents are very, very small. And here's a critical current plot, and you can see that we have something of the order of milliamps per centimeter squared, whereas at ambient pressure, one has a critical current that is kiloamp per centimeter square. So orders of magnitude lower here in this region. Again, pointing to the fact that we don't have a bulk superconducting state anymore. And finally, I would like to note that in the high pressure regime, we actually see two transitions. And we believe those two transitions are due to antiferromagnetic order, not ferromagnetic order, as one would expect from a uranium-based triplet superconductor. And why is that? First, if we have two transitions, that is inconsistent with a simple ferromagnetic state. If you have a ferromagnetic state, you already break that symmetry. All the spins are pointing towards one direction. Maybe you can have a rotation of the spins, but that would be a crossover. It wouldn't break any additional symmetries. But here, clearly, we see two peaks in heat capacity and anomalies in resistivity. And at the transitions, actually, the resistance goes up on cooling, which is also inconsistent with ferromagnetic order. And if we remember the Fisher-Langer relationship, that gives us that the derivative of the resistance with respect to temperature is similar to the heat capacity. The heat capacity is always positive, so one would expect that the resistance would go down on cooling through the transition temperature, but that is not the case here. And this has been seen before, of course, but only in antiferromagnetic systems. You may have a super zone gap, for example. In that case, the resistance is expected to go up, which means that the ordering vector for this magnetic order may not be commensurate with the lattice. I would like also to note that we're not the only ones getting to this conclusion. The Japanese group, and this is a paper led by Aoki, they also, from experiments not under pressure, but in high magnetic fields, they also come to the conclusion that antiferromagnetism is a likely possibility, actually. But this is very complicated now, right? Because we had this idea that this system is close to a ferromagnetic instability, is a spin triplet superconductor, just like uranium, germanium 2, uranium, cobalt, germanium. But that doesn't seem to be quite the case. And actually, this reminds me more of uranium, ruthenium 2, silicon 2, which is an antiferromagnetic or close to an antiferromagnetic transition. And again, cerium, rhodium, 5, which is also close to an antiferromagnetic instability. And I would like to point out that very recent results from Andrea Severin's group using X-ray scattering really shed light on this. So here are our results on a variety of materials from the uranium transition metal to silicon 2 family. And the point here is that once one increases the 5F2 configuration of uranium, and so here going, for example, from iron to palladium, actually one has more localized F electrons. So this is somewhat counterintuitive, but because in particular under pressure here for uranium, ruthenium to silicon 2, under pressure we tend to think that we're increasing hybridization, right, from the Doniak phase diagram, but that doesn't take into account the valence of uranium. So if the valence is changing and that's changing the localization, you may actually go the other way. So you may go towards an antiferromagnetic state. So the point here is that for 5F2, the 5F2 state of uranium, the F electrons are more localized and you have smaller J's, again, thinking of the Doniak phase diagram, or even higher U, which is the on-site Coulomb interaction. So taking this to uranium tellurium 2, we have done in collaboration with Gilberto Fabris at the Advanced Photon Source facility, measurements on uranium tellurium 2 under pressure. And here you can see the L3 edge of uranium and the Zane spectra compared to uranium cadmium 11, which is a good 3+ reference, and uranium fluorine 4, which is a good 4+ reference. So the Zane spectrum of uranium tellurium 2 is somewhere in the middle. So we don't have a really 3+, neither nor of a 4+ configuration, but it is closer to a 4+ configuration. So we can think that we have a mostly 5F2 configuration with a little bit of 5F3. And if we remember the discussion just now from the 1-2 family, that means that the system is somewhat hybridized. But under pressure, and this is panel B, there is a small but finite shift towards higher energies, meaning that we have then a more 5F2 configuration. So we're going with pressure towards a 4+, full 4+ configuration. So this makes a lot of sense, right? If we apply pressure here, we're going to a 4+ configuration. So 5F2, which is more localized, and then we have magnetic order. Again, counterintuitive if you just think of pressure as increasing hybridization, but not counterintuitive if you take the valence into account. And finally here, the energy shift or the valence shift, depending on what you want to look at, it starts to increase more pronounced above PC1. So when we have you know, the magnetic order extrapolating to what we think is a quantum critical point. Above that, we have a valence that goes towards 4+. So this all makes sense to me, and this actually helps us understand some of the outstanding questions in the field, because now we know that we may actually be close to a quantum critical point. We may be close to an antiferromagnetic instability, and that changes a lot of the constraints. And if we look at all the irreducible representations of this space group, there are many possible combinations here. So we know that we have two superconducting transition temperatures. So we have to choose two of these irreducible representations, but it's not so easy, right? We need extra experimental input. And now we have that. And I want to point out that even before our paper came out, initial DFT plus U calculations, and this is density functional theory calculations, considering an on-site Coulomb interaction U, try to find various combinations or configurations of the spins. Again, remembering that we have this chain along the A-axis and the dimers along the C-axis. And here in figure C, you can see that it's actually not energetically favorable for the system at high U, Coulomb U, to be in the ferromagnetic state. And this is very in line with what we see experimentally. So now, again, remember with pressure here, we are actually increasing the Coulomb U, not decreasing it. So the system is becoming more localized, and we don't see a ferromagnetic state. We see an antiferromagnetic state. And more recent calculations using tight binding model, DFT, and periodic Anderson model, they used everything they could. And this paper is really nice. I recommend for those of you who are interested in the subject. They take our results into account, and they do show that it's very possible and actually energetically favorable for an AG state, which is a singlet state, to occur as a function of pressure. Here, P is pressure. It's a theory paper. I have no idea what the units are here, but this is an increasing pressure regime where an AG singlet state may be favorable. So it could be that you have indeed under pressure a mixed, even an odd parity superconducting states. And this is the temperature pressure phase diagram obtained in this paper, and you can see the evolution of the possible order parameters under pressure. I should say, unfortunately, this is not a done deal, because there is one piece of information that goes against this nice scenario that I like. So going back to the possible irreducible representations, we know that the order parameter is a two-component order parameter, but this is the piece of information that doesn't quite fit so far. These are polar Kerr effect measurements, and without getting into too many details, because I'm running out of time, at TC, at the superconducting transition temperature, there is a finite Kerr rotation, which is associated with time reversal symmetry breaking. On top of that, this is field trainable along the C-axis. And this may get a little technical right now, but field along the C-axis transforms as a B1G component. And the only way to have a two-component order parameter with this B1G coupling between them is to have a order parameter that is a B3U plus IB2U, meaning that the order parameter has to be fully triplet, no A1G allowed. So right now, this is still an outstanding question, and I am looking forward to further discussions. The second outstanding question is sample dependence, as I alluded to during the talk a few times. Sample dependence is an issue that is pretty much always present, right, in condensed matter physics. These samples are grown by chemical vapor transport. So on the hot end, we have a mixture of uranium, tellurium, and iodine. And iodine is the chemical vapor transport agent here. But the interesting thing is that we don't start with a stoichiometric amount of tellurium. So it's not uranium-1, tellurium-2. No, it's uranium-1, tellurium 1.5, or something nearby. So why is that? We don't know yet. There is an early heat capacity study comparing chemical vapor transport samples that I just mentioned to you with flux samples. So here F or the red circles are data from a flux grown sample, and there is absolutely no superconducting transition temperature. So there's clearly something going on there. More recent results showed a spread of TCs depending on the initial tellurium concentration, for example. We also know that depending on the thermal gradient, that can change too. The interesting point of this recent paper is that TC scaled with gamma. So higher TCs are actually inversely proportional. So higher TCs, lower gammas. So in principle, naively, you can think, oh, if I have the cleanest sample possible, TC will be even higher than 1.8 Kelvin, and gamma will go to 0, but that remains to be seen. And interestingly, one of these samples actually has a higher resistivity or resistive TC compared to the bulk one. So again, all interesting, very interesting actually, material science problems that we now have to explore. And again, I'm very excited about this material. So let me thank my collaborators. Without them, this work would not have existed. This is the SCAS team, or strongly correlated electron systems team at Los Alamos here on the left. And in particular, Sean has done an amazing job with the pressure cells at very low temperatures, 100 millikelvin, using an adiabatic magnetization fridge. Fred grew a lot of these samples. He was a PhD student from Brazil working with us here for a year. And on the theory side, Morten and Rafael did the phenomenological model. And at APS, Gilberto did those really nice Zane's measurements. So with that, I would like to have one more slide for you with an advertisement. We have quite a few postdoc positions open right now and available. So if you are a student defending a thesis soon, or a postdoc looking for your next appointment, please contact me. Here's my email, which is not working right now apparently because the Lano network is down, but hopefully soon it will be. And with that, I would like to thank you for your attention.
Thank you very much, Priscilla. Very nice presentation. This is really beautiful work.
Thank you.
Let's open this up for discussion. There's already a question in the chat box. Just unmute yourself, Urshan.
Thank you for this beautiful talk. Really, it was very comprehensive and very detailed. I was wondering how much your results are sensitive to sample impurities or non-stoichiometries or defects. In other words, how reproducible are these results?
So yeah, that is a good question. There are many answers to that, depending on what exactly we're referring to. Let's say that for all the samples we have grown so far, they all have a residual gamma. So again, this is still an open question. It is not impossible that the samples are still in the early stages of sample preparation, and this gamma is not intrinsic. So that's one aspect. For the work under pressure, the results are extremely robust. Yes, there is some sample dependence, but it's very small compared to the overall behavior that I showed here. So, and you know, again, we're not the only group to apply pressure to this material. There is always a kink at 0.2, and above this kink, one transition goes up and the other one goes down. That is extremely robust. 3 different groups observed that. I should mention that compared to this result, for example, I think we did go a step further in the sense that we were able to look at this region around 1.5 GPa and really see what I showed you, see this coexistence region. But I would say the results under pressure are fairly reproducible. One open question that I didn't have time to really discuss is how robust the superconducting state is against impurities in general, and in particular, if you dope the system with, let's say, thorium, or if you dope the chalcogenide site with sulfur or selenium, and we're still investigating that. I don't have an answer for you right now, but that will be very useful to also to shed light on whether this is a triplet state or not.
Thank you.
More questions?
I have a question. Can I ask, or?
Go ahead, Shanti.
Yeah, so very nice talk, Priscilla. Really enjoyed it. So I have a question following the previous question about the pressure studies. So how do we know that there are not multiple structural phases exist at these low temperatures? Do we have any, I know it's hard to do structural studies at these low temperatures, but how do we know that there are not multiple phases that are giving, because we may have both coexistence of phases, or we may have pressure gradient that causes a slight pressure gradient. So how would you exclude that possibility?
Right. So again, the fact that going back to the fact that a lot of the groups, or all of the groups that studied this material under pressure got to the same conclusion in phase diagram, that tells me that pressure and homogeneity may not be playing a huge role here. In uranium, ruthenium 2, silicon 2, here is actually all the phase diagrams from all these references with different pressure media. And you can really see the difference there, right? Depending on whether you use argon or helium, which are pretty hydrostatic, or fluorinert, which is not very, there is a huge difference. And we don't see that. So that's one aspect. The other aspect is that even though we do not have measurements yet below 1.7 Kelvin, there are 2 reports. So one down to 2.7 Kelvin using neutron diffraction. They didn't see any differences in the in the crystal structure. And our results also with the L3 Zane's edge doesn't show dramatic changes under pressure. Everything's very smooth. But yes, we could only go down to 1.7 Kelvin. So if we could go below that, that would be really fantastic to demonstrate that there are no structural changes in the superconducting state.
No, that's good, because I think a lot of these features are happening above 1.7 K. So yeah, I guess that's reasonably
Right, for the magnetic part, yeah, and yeah, you're right. At 1 GPa, we have, yeah, the superconducting state, TC1 at least, is above 1.7.
Perhaps a related question. You're seeing remarkable changes over very small pressure ranges, in some cases almost a fraction of a kilobar. So what kind of strains are we talking about, just based on the bulk modulus? You know, how much volumetric compression are we talking about to induce these transitions?
That's a good question. I don't know. So we don't know what the bulk modulus of this particular material is at this point. So I wouldn't have a number off the top of my head for you. But I agree completely that this is not very usual, and we're actually very lucky because we can do most of the measurements in a piston clamp cell.
Yeah.
But yeah, I don't have an answer for you.
Okay, there's another question. White Walk? Go ahead.
Yeah. So one of the questions was, can you irradiate these things, like say with protons, to introduce defects? That way you don't change the crystal structure. And then to see if you can tell the difference between a single state or triplet state, depending on the behavior of TC.
That should be very possible. As far as I know, it has not been done yet.
Interesting. Thank you.
Thanks. More questions?
Could I ask a question?
Go ahead.
Many years ago, it was reported that pure uranium superconducts at 0.8 Kelvin in the beta phase, and with a little pressure, you can push TC up to 2.5 Kelvin. So T.F. Smith did that work in 1973. Has anyone done any more recent work on pure uranium? Maybe it's also a P-wave superconductor.
That's an interesting point. I haven't been following the more recent literature on pure uranium, to be honest. But that is an interesting point. So it is. I cannot even remember whether the critical field there is large, though. I thought it was pretty small. Is that correct?
Yeah, I don't know that offhand, but I just know it's been reported as being in the beta phase and alpha phase being superconducting.
Yeah, I should look into that.
Okay.
Thanks. Any more questions?
Yes, one last thing.
Go ahead.
Stella, have you thought about doing like fermiology at below the superconducting before this, or like in non-superconducting state? These are pretty achievable pressures for them to doing fermiology in high magnetic field to see that how the Fermi surface of these things are. If you see like double super, for example, something that explained the presence of two superconducting phase.
Right. So actually a lot of that has been done even at ambient pressure, but no quantum oscillations have been observed so far, which is a little surprising to me. At fields below 20 Tesla, actually the magnetoresistance is not very large. So that could be related to a couple of things. Well, first, if the sample is not perfect, you may have scattering from disorder, messing up things for you. But also, we know that there are strong magnetic fluctuations in this material. And if you have strong magnetic fluctuations, you may not get to a regime where omega c tau is larger than 1. So unfortunately, we don't have fermiology from quantum oscillations yet. But that's an interesting point. It could be maybe, if you're optimistic, that under pressure, you might be able to, especially, let's say at 2 GPa, when you're away from the quantum critical point, you may be able to see quantum oscillations, but then you have the magnetic state there in your way, right? So that's still an open question, and I think those measurements will be done soon with pressure.
Awesome, thank you.
Thank you. Any more questions or comments? If not, thank you very much, Priscilla, for a very nice talk. And thank you all for joining us.
Thank you very much.